All right, this is Physics 1B, the last hour of class for September 28th. I wanted to start off by talking about the greenhouse effect. And we're going to use just this PhET simulation from this website. To do this, you're welcome to play with it yourself. So what do we have here? So there's photons represented by these dots right here. There's different types of photons. There's sunlight photons, and there are infrared photons. The infrared photons are coming from the warm Earth here. Okay, the Earth at this location looks like it's about 58 degrees Fahrenheit, and I don't know why it's in Fahrenheit. It's kind of funny, but 290 Kelvin as well. And so you're getting these photons that are basically coming from the red ones. I don't know if you can tell, but the red ones are all coming from the ground. The yellow ones are all coming from space. Okay. And was there a question? So I heard someone cue their mic. If you do have a question, feel free to say something. So how does this work? Well, the sun emits radiation. It comes to the Earth, right? And then the Earth re-radiates some of that energy that comes in. Now, if all of the energy that came into the Earth was then reflected back out, like let's say, for example, if the surface of the Earth, if we had no atmosphere and the surface of the Earth was like a mirror, then basically all the energy that comes in would be reflected back out, and the Earth would not really heat up very much. Okay. Our Earth, however, has an atmosphere, and that atmosphere tends to trap some of that heat. And that's a good thing. The greenhouse effect is definitely a good thing. It's one of the things that keeps our planet warm. It also is related to how an actual greenhouse works, in terms of, greenhouses are constructed of a type of glass that will allow sunlight to pass in, but when the sunlight, when the IR or the infrared photons come back up from the plants and stuff, they kind of get trapped in the greenhouse, and so the greenhouse can stay warm all year long, and it's a good way to grow plants during the winter and stuff like that, right? Okay, so what we can do right here is we can change the greenhouse gas concentration. So what's the greenhouse gas? Specifically, in this case, it's basically carbon dioxide, stuff like H2O, CH4, which is methane, and then N2O. What is this? Nitrous oxide? What is N2O? What's the name of that? I don't know that one. Is it nitrous oxide? I don't know. Someone's typing. Maybe they'll tell us. Feel free to look up on the internet too. All right. So the temperature here is basically just fluctuating a little bit, but it's staying around 60 degrees Fahrenheit, right? See a lot of people typing. I haven't seen the answer yet. Tell us what N2O is. Help us out. All right, so let's see what happens here then if we increase the greenhouse gas concentration. So if we increase the amount of greenhouse gases, nitrous oxide, so that is what it is. What ends up happening? So I remember this being a little bit different. Maybe, is it this one? Is this the one I want to look at? Okay, we're going to come back to that in a second. Did anything change? As we make this thing go up higher and higher, what did we see? What changes? The temperature basically goes up. Okay. How can you observe that right here? Did anyone notice what changed when I raised that on the picture? The number of infrared went up. So that makes sense because the temperature itself is going up. So the hotter the surface is, the more infrared radiation we're going to get, right? What else happens though? Is there anything else that's happening? View all photons is a little bit too much, right? Is there anything else that's happening? What happens? Let's just go down a lot lower. So the greenhouse gas concentration goes down. They're moving faster, okay. Temperature's going down. What's happening to all these molecules? What's happening to all the red ones? Most of them are they're kind of escaping, right? Now, every once in a while, you'll see that they'll bounce down. This is what I want you to notice, is notice how some of these bounce downwards. See that one? That one's coming back, right? That one came back. Most of them are escaping though. See, we'll track them. Oh, that one came back. They're going. A lot of them are getting out. A lot of them are escaping, right? So the temperature's low because there's most of the energy that's coming from the surface of the planet is basically escaping the planet at this point, right? But if we add more stuff into the atmosphere, so what is this? This is around. This is supposed to 1750. There's a little like farmhouse or something like that, and then we can go to today. The difference is that you'll notice a lot more of these red molecules bounce back down. Okay, and part of the reason why that's happening is because these molecules like CO2, they will absorb. So imagine there's like a gas molecule up here, right? Infrared photon comes along and eventually it hits a gas molecule. What does the gas molecule do? It re-radiates it back downwards, basically, right? So the greenhouse effect is basically just the atmosphere itself absorbs some of the infrared radiation coming from the surface, and it holds it in, right? And that's part of what keeps our planet warm. That's part of what keeps our planet warm is if we have enough greenhouse gases, it'll keep our planet warm. The problem is that if we have too much of it, and this is something you may have heard before, if we put too much carbon dioxide into our atmosphere, if we put too much of these other substances into our atmosphere, so methane comes from like cow farts, right? Carbon dioxide comes from us breathing. H2O comes from water vapor, and then nitrous oxide. I don't know what natural processes make this happen, but as we burn fossil fuels, we dump a lot more carbon dioxide into the atmosphere. And the effect of that is just that we create this blanket layer of CO2, and the effect is that a lot of the energy coming from the surface just gets trapped and not re-emitted out into space. And the effect of that is that it warms the planet. The temperature just starts to slowly increase. And if we have a ton of greenhouse gases in the atmosphere, a lot of carbon dioxide, the temperature of the planet just rises. And that's the phenomenon that we've kind of been experiencing on our planet over the last 100 years or so as we've industrialized. So this thing occurred in the 1950s called the Industrial Revolution, during which kings and queens all across the world kind of fell to kind of a workers' revolution where we became able to have more control over the way things are produced, and corporations could make things. The problem was that they started to emit lots of fossil fuels. They used a lot of fossil fuels to do this, to run the factories, and it emitted a lot of CO2. And the effect is that we've been having the temperature of the planet kind of grow over time. Now, why does this happen specifically with greenhouse gases? Like, why does it matter that we put CO2 in the atmosphere? So that's what this is for. So this allows us to, I believe, emit photons. We can take a gas right here. Let's start with CO2. We can take a gas right here, and we can allow it to emit photons. And this is supposed to show you that sometimes these photons get absorbed, and sometimes these photons pass right through, basically. Okay? And this is specifically for CO2. If we change it to CH4, similar thing happens. Sometimes the photons gets absorbed and then re-emitted back down with CH4. This is like carbon and then 4 hydrogens, or methane. And then H2O, similar thing. We can check nitrogen. I think all of these will, to some extent, absorb these photons, right? Maybe nitrogen won't. Looks like nitrogen isn't having much of an effect here, right? It looks like nitrogen is not absorbing these photons for some reason. What about oxygen? So what does this tell you? These guys, not so much of a problem. We can have a lot of oxygen in our atmosphere. It's not gonna absorb these photons in the same way. But when we pump more carbon dioxide into the atmosphere, the carbon dioxide will have the effect of trapping some of the heat. And it's okay to trap some heat. You just don't want to trap too much of it. So now the next thing we can do is we can actually make an atmosphere here. So we can put a bunch of CO2, we can put a bunch of oxygen, maybe some nitrogen, maybe a little water. And then we can force this thing to start emitting photons. And so now the net effect is going to be that we're getting all these photons that are coming from the Earth, and you can think of it as any of the photons you see bounce back to the left are getting trapped, and any of the photons you see pass through are not getting trapped, right? And so, I don't know, does this make it clear enough? If you get enough of these CO2, all the ones that are wiggling, you get enough of those in your atmosphere, then you're going to have the temperature of your planet go up, basically. And that's kind of what the greenhouse effect is, effectively. We never added clouds. I can only add 3 clouds. That's the most clouds we can add here. All right, did that make any sense? I wonder if it would have made more sense if I just drew a bunch of pictures. But this image, I kind of wish it would show like some... I wish you could add this piece to the first picture here, so you can see that the reason why some of these infrared molecules are bouncing back down like that one did there, and then it's bouncing back around, is because they're interacting with the... It's weird that it's become political. Yeah, everything becomes political to some extent. What's this one? Number of... Oh, there we go. Here we go. Oh, look at that. That's kind of cool. So let's see what happens here. The temperature already got really high. Can I reset it? Okay. So here you have just the same thing as the first picture, but what we can do is you can add in a piece of glass. And the idea is that this glass is designed to be kind of like a little bit translucent to the red ones, so that some of the red ones reflect back and some of them don't. And that's how you can trap some energy down here. You can see the temperature goes up. This is just a greenhouse effect. The funny thing to me about the greenhouse effect is that I don't think that, you know, you've got people that deny that global warming's happening, whatever. We can, I don't want to be too political or anything like that, but I don't think that anybody would deny that a greenhouse works. Right? Would you guys agree with that? Do you think anyone would deny that greenhouses are effective at growing plants in the wintertime? No. I mean, that's easy to prove. Like, it's not... I mean, when I was in college, I remember we built a greenhouse, and we grew a bunch of plants because we were in Santa Fe, where it gets really cold in the winter, and, you know, we built a greenhouse. It works just fine. They're not hard to build, right? So no one's going to deny that the greenhouse effect is a real thing. The question is, and I think this is where the political part of it comes, is the addition of extra CO2 molecules to the atmosphere something that has been driven by humanity? Like, is it caused by us? That's the first question. And so a lot of people would say, no, it's not caused by us. It's just a natural warming and cooling cycle of the planet. And then the other point would be, is what humans doing, is what you said your cousin grows plants with a wink face. I like that. Is what we've been doing having a measurable impact on the change in our climate, right? I think those are the things that people debate about. Is number one, are we responsible for this? And number two, is what we're doing having a measurable impact? And I think that scientists would tell you, yeah, and people that have a vested interest in wanting to keep polluting the atmosphere will tell you no. They're telling you, no, it's not that big of a deal. Don't worry about it. And in reality, I think, as with anything else, it's just a matter of serving self-interests, right? Like, if I'm running a company that relies on burning fossil fuels to make money, you know, if I'm selling oil, or if I'm running a oil refinery or whatever, if I'm running a power plant that operates off of fossil fuels, like if I'm burning coal to produce power and then I'm selling that power to consumers, I'm going to try to keep playing that game as long as I can, right? Like, if I run a power company, I'm just going to keep running that power company until someone tells me to stop doing it, right? And I think that's normal, right? Like, that's the nature of human beings, that if they can find a way to make money, they're going to keep doing that until someone shows them definitively that what they're doing is going to create problems for everyone. And then to some extent, you have to disincentivize it. So, you know, I think we're in a weird spot right now where, yeah, like, as Cam says, it's weird that it's become political, but I think everything becomes political when it involves people's jobs, when it involves people's ability to make money. So I don't know. What do y'all think about this? Hmm. I don't know what mhm. What do people think? The answer to that question. What is it that misleads people? That might even have degrees in science or engineering. Hmm. Or they find resources that are giving them kind of false conclusions that are based on, like you say, maybe a different interpretation that might be wrong, or it might be flawed, or it might have some assumptions that are not good. But and I think it's really easy to find something that you believe in. You know, like it's. I was watching a documentary the other day, and they were talking about how, if you type like, is climate change, they said, like, if you type this into your browser in different parts of the country, you're gonna get a different answer, like for what comes up here, right? um, like, it might say, this guy, that doesn't even do it, but like, I think a lot of it is like, where do you get your information from, you know like, what do you read? Because, like, there are scholarly articles out there that will tell you that, you know climate change either isn't a problem, or that, and I know at El Camino there's a teacher who, he gives an assignment to his students to write a paper about climate change, and to I think he encourages them to prove that it's not real, or that it's not caused by humans or something like that. I don't know. And you know, it's pretty easy to go find information out there that will support your views. I think these days, with how little, like, quality control there is for the, like, type of information you can find. Right? Like, I can go to YouTube and I can find videos about the Earth being flat. You know, and I remember, like, Kyrie Irving, who's a basketball player, uh, was kind of famous for saying something on Twitter about how he believed the Earth was flat, and then that, like, later on he was interviewed by someone, and that person was, like, asking, like, do you still believe in this? And he goes, no, I talked to some people. I realized that, I just got stuck in, like, this, like, rabbit hole of YouTube videos, and those YouTube videos convinced him the Earth was flat, and, he thought that it was just, like, a conspiracy, like, whatever. But then, when he broadened his mind and he kind of, like, opened his eyes, like, he realized that those videos were actually false. So I think a lot of this stuff just comes from the ability to convince yourself of whatever you want, given your ability to put yourself in a bubble, and whether that occurs through your friends. I don't want to blame anything. I'm not trying to blame YouTube. I'm not going to blame social media or anything like that. I just mean, how do you personally get your information, right? Whether it be through reading websites, or reading the newspaper, or reading your Facebook feed, it doesn't matter. Whatever way you want to convince yourself of something, you can do that. And people will always be skeptical, regardless. This stuff's real. And it's legitimately a problem that if we don't make some kind of change to the way that we produce energy, we don't make some kind of change to the way in which we eat food, that, long term, we may have lasting impact on our planet. And, God. Yeah. 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 Yeah, for sure. Let me see if I can show you some example of that from my own feed for news. Just oh yeah, it's hard. It's hard to beat these computer algorithms for sure, especially when they figure out what you like and they just keep giving it to you. I was going to show you guys an example of this for me personally. Maybe it only shows up on my phone. When I pull up Google News on my phone, it always defaults to a version of Google News that's like this. Will it do it? Yeah, there it is. It gives so when I pull up, I don't know why it does this on my phone and it doesn't do it on my computer, but like when I pull up Google News on my phone, this is always what I get. Okay, and it will be nothing but things that I read a lot about. Okay, so quantum entanglement realized between distant objects. This is an interesting topic. Would this show up for someone that's like just, I don't know, a trucker from Oklahoma or something like that? No, they wouldn't get this. Asian Empires defended, like, all the stuff that shows up on this feed is stuff that I want to read about, probably. And in reality, I don't. I'd rather be exposed to things that I'm not interested in, because that's where you can learn more about things, right? But it doesn't change the fact that Google News, YouTube, Facebook, every single one of them uses what you described as an algorithm, right, Danny? That basically bubbles you out from experiencing ideas that might challenge you. Barron's, yeah, exactly. That's right. It gets better the more that you interact with it, right? And well, and then they even ask you questions during the advertisements now too, right? Because they're trying to get as much information as they can to like tailor all the right ads to you. Okay, a couple things people said in the chat is Ruja said people don't like to change their beliefs. They'd rather to try to disprove anything that goes against their beliefs. That's really true. That's a really good point. And then Ange says that's on being stubborn. Cam says, I don't think people think with a scientific mind. Yeah, definitely not. It's not natural to think with a scientific mind. It has to be developed over time, right? So that you can become skeptical. Baron says to watch The Social Dilemma on Netflix if you want to see how news and social media can become skewed. Yeah, it's really good. I watched that, actually, Baron. That's actually what I was talking about. It's pretty good. And there's a lot of other documentaries out there about similar topics. There's one about the 2016 election, all this kind of stuff. I don't want to sit around and just recommend stuff for you guys to watch. I'm sure you guys have plenty of things you can try to watch. Tom says you get PS5 stuff on Google News. Yeah. You say you clicked once on a meteor coming close to Earth and that's all you got for a week. That's so true. Yep. I get all kinds of things about dark matter. With the way that my feed talks about dark matter, you think they're discovering something new every week. In reality, I try to read each article and they don't have any new information. YouTube recommendations, Kenny is saying it's like that. Yep, watch one video and that's all you get. That's totally true. Watch one video about the Holocaust not being real and you're going to get a bunch of videos about the Holocaust not being real. Same thing about global warming or any of these other things. And, you know, I do want to emphasize that I don't by any means want to try to make you guys feel like you need to think a certain way or do a certain thing or etc. Like, you're all free to think as you will, and I don't have all the answers. I'm just a guy that teaches at a community college. You know, all I can offer you is just perspective, but I do think the greenhouse effect is something we need to care about. And I mean, just to tell you my personal like what I think, and this is probably just completely out there. When I was a kid, I remember reading in like a textbook about the difference between renewable energy versus non-renewable energy. You guys know what that means, right? What's renewable energy? Green energy. Yeah. Right. Exactly. If I take some mass of coal and I burn it, I'm gonna get all the energy I can out of burning it, and then once it's burned up, it's gone. But stuff like solar energy, wind energy, tidal energy, geothermal energy, these are all types of energy that you can use and reuse forever. So if you go and you put a bunch of money into putting solar panels on top of your home, then that will pay off in the long term, because eventually you will literally be able to sell power back to the power company. Did you guys know that? If you get enough solar going and you don't use enough of your energy, that you can quite literally sell money. You can make money off of generating solar power on your house by selling that energy back to the grid, which is just incredible. And you know, I think I'm naive. I think I'm optimistic. I don't know if those are bad things, but when I first read about these things, I was like, if you knew setting out to make a power plant that you could make a power plant that either generated energy from the sun or you generated energy from something you have to keep buying, which is coal, wouldn't you always choose to use the one that generates energy from the sun? Because the sun's not going anywhere. Like, to me, that just makes sense. But the reality is that the cost that it would take to produce a plant to make solar energy versus the cost and like what you can make off of selling like electricity that you generate by burning coal and fossil fuels, you're going to make a lot more money currently by selling fossil fuels. And there's this guy, he went to the school I went to. His name is T. Boone Pickens. I don't know if you've heard that name before, but he made all his money in the oil industry. And he tried in Texas, in West Texas, where there's just a ton of wind. He basically tried to see if he could beat out the fossil fuel energy producers, the ones that were making money off of burning fossil fuels. And he was initially somewhat successful. He built a lot of wind turbines and stuff like that, and he was able to make a decent amount of money. But then something happened in the 2000s, the late 90s, where there was this huge discovery of these natural gas deposits beneath Texas under what's called I forget what it's called, but basically they found that they could find natural gas in Texas, and it was cheap. I mean, they could drill this stuff up. It cost them almost nothing to drill it up, and then they could burn that fossil fuel, burn that natural gas, and sell it to make electricity. And it ran them out of business, basically. The discovery of that natural resource that they could just pump out of the ground and then burn and then turn into electricity, and also, but you could also take that natural gas and turn it into petroleum products, right? He couldn't beat them, you know? And at the end of the day, in a capitalistic society, that's what it takes to make changes. Is you have to find a way to be profitable in producing these things, you know? That's it. At the end of the day, if you can't beat the people that are making money off of electricity production via coal by producing it with another method, you're going to lose. And I think the good thing is that we're kind of coming around the bend on this stuff, where it will unquestionably cost more and more over time to produce oil, because we are eventually going to kind of, the rate at which we can gather and produce the oil versus the rate at which we consume it is changing over time. So eventually it's going to cost more. And there'll be a breaking point, right? Where things like solar energy, wind energy, geothermal energy will quite simply be more profitable. And when that happens, it'll change overnight. It'll be no different than what happened when we went from regular old telephones to cell phones, right? To smartphones. You know, like that was a change that occurred within a year or two. That you went from hardly anyone has cell phones in the 90s to the 2000s where everyone has them, you know? Not only did it occur like that, there were countries in which they didn't have, there were countries in which you didn't even have like a grid for the regular cell phone, the regular like landline like phone networks, and they skipped over the technology. They just went straight to cell phones, right? So I do think there's hope, in the sense that eventually, and hopefully, we make the change over to kind of like green energy before we just completely ruin the planet, because that's what's going to happen, you know? And another thing about it is, like, it shouldn't be that surprising that if you drive by a factory and you see big plumes of gray smoke going up into the air, that's probably not a good thing. You know what I mean? Like, it's not that complicated. That if you see a big plume of black smoke coming out of something, that's probably not good for the air we breathe. It's probably not good for the environment. And I don't think there's much of a doubt that dumping a bunch of black smoke into the air is bad for us. But the question is, does it actually do this? Is it actually increasing the temperature? And if it does it matter? Because for some people, they might think, oh, it's just getting hotter. It's not that big of a deal. Cam says, well, there's only hope if we get to that point before the tipping point for climate change. Yeah, you're right, Cam. And hopefully we'll. I think we will. producing green technology is becoming more and more cheap. Our solar panels are getting better. Even our wind energy is getting better too. So people say that making electric cars is just as bad as having normal gas cars. Also, how do we deal with the rare minerals running out for those cars? Well, see, that's the thing, Tom. It makes a lot of sense to use gasoline for something that's going to move around, right? It makes a lot of sense because you carry your fuel with you and you go to a fueling station, you fill it up. What doesn't make sense is then to also use that same electricity to use that same gasoline, that same fossil fuel to also produce electricity, because then you're just going to run out even faster, right, Tom? Does that make sense? Yeah, making the electric car is just as bad as having normal gas cars. The other thing about electric cars is that it takes energy to produce them. Number one, that probably consumes fossil fuels. The other thing is, like, when you actually power up the car. Sorry, I didn't mean to interrupt, but when you actually are charging the car, you have to think about where that energy is coming from. If you're charging your car by like plugging it into your wall socket or like something in your garage, then you're basically just charging your car with fossil fuels, you know, because like that's where the energy is coming from. Like, I mean, the energy most of you are using right now, if you have a computer that's plugged into the wall, it's coming from burning fossil fuels, right? Or from nuclear power or something like that. Now, I want to get back to nuclear energy, by the way. That was the first thing. When I asked what renewable energy was, the first answer I got from Ruja was nuclear energy. Nuclear energy is technically not a renewable energy. It is, however, a very, like, it's going to take a long time to run out of it, you know? It's something that lasts for a really long time. It has issues. It produces a lot of waste heat, and that waste heat can cause problems with ecosystems, but there's a lot of promising ideas with nuclear fuels and nuclear energy that it can be used in combination with like solar and with wind. But nuclear energy you shouldn't be too scared about it. It feels like there was kind of a lot of negative press that nuclear energy got for a really long time, but so the nuclear waste itself. So the thing to understand about nuclear energy is, like, when you actually produce the energy, since it's the energy that's contained within an atom, you don't use very much stuff, and the waste that you produce, you can kind of bury it underground in lead and concrete, and it can be pretty safe. People are scared of nuclear energy because when it goes bad, it goes really bad. That's true, Ruja. That's actually right. And then Cam mentions Fukushima, Chernobyl. Yep. So this is a whole other discussion we could get into, and it's worth talking about, but all of those are design issues, right? All of those, the issues that occur with Fukushima were that it was designed, or it was in a place that was like either on a fault line or in a place that like they knew you were going to get tsunamis, etc. So there's other models that you can use for designing nuclear reactors that have automatic like fail-safe shutdowns. If you've ever heard of this, yep, Rue just said it right as I was saying, a molten salt reactor, exactly. If you go look at those, they have like automatic fail-safes that make it kind of impossible to have a nuclear meltdown. The problem is getting someone to actually build one, and anyway, so long story short, burning fossil fuels for electricity at too high of levels is bad. It's okay to do some of it, so maybe long term we could reserve fossil fuels for just running our cars. But your high school chemistry teacher would talk about the molten salt reactors, Ruja. That's cool. There's some really good YouTube, like TED Talks and stuff about thorium salt reactors that are definitely worth. We could watch some of those videos too. The meat industry and their greenhouse gases. Yeah, so I mentioned that in passing, that like one of the things we might have to change is what we eat. But you know what I'd rather do? I'd rather not change what we eat and just fix all the other stuff so that we can so that we can keep eating meat, even though supposedly eating meat is like extremely detrimental to you, and leads to like shorter lifespans and all that kind of stuff. Like, meat's really good. One thing I think that's really interesting that's happened in relation to the meat industry, and I think that this what I'm about to say may have some kind of long term effect, is like athletes are now realizing, like a lot of like really high end professional athletes are realizing that relying on like plant based diets is like a lot better for you in terms of your ability to like, I don't know, convert the food you eat to energy or something like that. And so like vegan athletes, yeah, and they're not like vegan in the sense that they always eat that they never eat meat. So like I think Conor McGregor is an example of this, someone who like he used to eat nothing but meat before his matches, and then he switched over to a full vegan diet, and I think it kind of like affected his performance. Does that mean he doesn't eat meat ever? I don't think so. I think he eats meat all the time, but I think he, like when he's training for fights, if he fights anymore, does he even fight anymore? He switched to a plant-based diet at some point, and that's true. Yeah, I think that's I think that's kind of the idea, that your body's a lot better at converting plants into energy than it is at converting meat into energy, and that some of the energy just goes into the digestion or something like that, or the conversion. And definitely quickly getting into the fields of biology and chemistry that I know next to nothing about. But what I do know is that athletes have started to change this. And I think, like, you know, when athletes start doing things, it affects people. You know what I mean? Because, you know, we look up to athletes, and, we want to be like Mike, so to speak. Um, yeah, so that might have some kind of effect. I don't know if it's gonna have effect on me. I'll probably keep eating meat until the day I die because I'm an idiot. But um, I always think about wanting to become vegan or vegetarian. I know Bill Clinton switched over to being vegan after he had like multiple heart attacks, and he's apparently really healthy these days. But who knows? So we've talked about a lot of different things here, and we're kind of running out of time. So I want to at least try to solve this problem before we get out of here today. So let's get back to this, and yeah, all good stuff to talk about though. All right, so this is the problem we want to talk about. All right, so we're going to find the variation of atmospheric pressure with elevation in the Earth's atmosphere. We're going to make the assumption that at all elevations, the temperature is this, and that gravity is this. This isn't technically true, and maybe we could talk about how this might change if we altered what gravity is here. Okay, so my guess is it wouldn't change very much, whatever we're going to write in here. So I said we're going to do this with these two equations. The equation on the left was the ideal gas law equation. The equation on the right is the way in which pressure changes with depth. If this equation kind of looks weird to you, just to remind you, if you can write it in a different way. You can write it as dP is equal to negative rho times g times dy. And then you could say, well, what if I wanted to find just the pressure difference between 2 points? All I would need to do is to write this as negative rho times g times dy, but dy would just be the change in height, which we sometimes write as h. So that's all this equation is. It's a way of rewriting the variation of pressure with depth, which is this equation right here. All right. So really what we want to do here is we really just want to put these two equations together, okay? You'll notice that both of them have a rho in here. So what I'm going to do is I'm just going to take this rho and plug it in for that rho right there, okay? So we've got pressure times molar mass divided by R times T. That's rho. We multiply that times negative G, and this should technically then be equal to dP dy. Okay. This is a very short problem that we're going to do here, actually. This equation is a separable... Go ahead. Exactly. It's a separable differential equation. And how do you solve these kind of equations? Okay, that's right. So the pressure P is going to be a variable. The molar mass M is just going to be the molar mass of air. I believe we said in the previous problem the molar mass of air was 28.8. grams per mole. R is the gas constant. T in this problem we're going to fix at 0. But 0 degrees Celsius is about 273 Kelvin. And then little g, we're using 9.8. Well, that's written right here. We don't need to rewrite that. So M, R, and T are constants. P, however, is going to change. dP means it's going to change. So we'll put those together, and we'll write it like this. We're going to have dy times P, not P, that's the one thing that's changing, times M divided by RT. I guess we'll leave the negative sign right here, is equal to, oh, there's a G too, right? mg, molar mass times G divided by RT. We're multiplying the dy to the left-hand side. On the right-hand side, we'll have dP, and then we just divide by P. And that's what we want to solve. To do this, we're going to integrate both sides. Everything there is a constant. And let's say we integrate from, let's say that this is the ground, and we call the ground level y equal to 0. And we want to figure out how pressure varies up to some new height here, where we call our new height y. We could go from 0 to h or something if we want to, but let's just say we go from 0 to y. You know what? Let's go to y equal to h, from y equal to 0 to h, so that we have two different variables here. And then on the right-hand side, if we're integrating upwards, we'd want to integrate from the pressure at the bottom up to whatever the pressure at the new height is. Call it P prime or something like that. So I think in here we'd have to put the pressure at the surface, right? Where the pressure at the surface would be like 1 atmosphere, or okay. So then let's solve it. Right-hand side, h minus 0. It's just going to be h, so we'll have negative molar mass times G times h divided by big R times T. And this should be equal to this integral. What's that going to be? dP over P. So this is going to be the natural log of P prime minus the natural log of P naught. And then we can plug in, we could plug in numbers. We'll do that at the end though. mgh over RT. This should be equal to the natural log of the ratio, because when you do a log minus a log, it's the same thing as the ratio of P prime over P naught. P prime is just the pressure at some other height. Okay, so like the pressure right here is P prime. We're going to drop the prime at some point too. To solve this one, we need to raise both sides to the e power, or e to the power of. So we're going to get, on the left-hand side, we'll have that, and on the right-hand side, we just have P prime divided by P naught. We multiply the P naught to the left-hand side. We end up getting P naught times e to the negative mg over RT. That portion is a constant that we can calculate what this is, and then we multiply by the height h, and that should be equal to the pressure at that height. Okay, I called it P prime. I'm just now going to say that this is the pressure as a function of the height above the surface of the Earth. There we go. It varies like e to the negative this. So what does that look like? Well, if I were to plot let's see, we probably put height right here, right? This would be the height, or the y-axis, whatever you want to call it. And this would be your pressure. That when the height is very small, the pressure should be close to 1, right? Or P naught. How do I do this? So if that's 0, and this is P naught, that when h is 0, e to the 0 is 1. So the pressure value would be P naught. That's at
h equal to 0. H equal to 0 is right here, right? So this... Here, I didn't write that quite right. Yeah, this is h equal to 0, right? So this would represent p naught.
You know what I realized that's making this hard for me? Is that the h is the horizontal. Yeah. All right, let's fix that.
That's right, Tom. It's like, this doesn't... Something's wrong here. Okay. Yeah, if we're doing a function, then this is where the h should show up, and this is where the p should show up, right? Okay. So at h equal to 0, right here, the pressure is p naught. As h increases, since it's e to the negative all this stuff, it's going to exponentially decay like this. So there we go. That look right? It's not the best exponential equation, but that is what it's supposed to look like, right? Let me see here.
Yeah, this is their picture. Let's look at their picture here. So there's their picture. Yeah, it's pretty much the same. And they label it as like RT over mg and then 2RT over mg, etc. But yeah. So as you go up, what happens with the pressure? The pressure decreases. That's pretty much what it says. The higher you get above the atmosphere, up into the atmosphere, the more the pressure decreases, and this is the relationship. It's this exponential decay kind of thing. Okay? Do we want to talk about what would happen if g was a variable? What would g be?
Do you guys remember this from your Physics 1A? That g is equal to the gravitational constant times the mass of the Earth divided by the distance from the center of the Earth, where if this is the planet and this is the center, this is the radius of the Earth. If you're some height h above the surface of the planet here, then, or really y, then the value down here is going to be the radius of the Earth plus y whole squared.
So this would get a little trickier here, because if you plug that into there, right? We took our equation here. Do we really want to do this? I don't know. Are you guys interested? So we'd have to replace the g right here, right? So let's get rid of g. Let's take here. Let me see if I can grab all this stuff. Pull all that this way, and then we'll plug this in. Here. We'll make some more room. Yeah, we'd have to do that, right? Now these m's are different, right? But we could pull these out. These can be pulled out of the equation. Like that. A bunch of things that are a constant. And then in here we'd have this integral we have to do. This is a... So like the way I would do this, yeah, it's a trig integral, right? So you do y is equal to re tan theta or something like that, right? But
yeah, because it's a constant, so yeah, that probably would work, right? I was going to do binomial expansion, but that probably works, right? If you just say, yeah, I mean, say u equal to... I mean, do you even need to do this? Because this is just going to be... Here. You could just do it, yeah, because it's not... There's no... It's just a constant, right? So it's going to be something like... 1 over... Is that it? Is that all it is? Okay. Here, you know what we're going to do? We're going to take all of this junk and say... No. We just didn't do it. Yeah, we kind of skipped it. Let's just let alpha be equal to all that stuff so that we can make this a little simpler on ourselves here. So now we'd have, this would just be alpha times this. And actually, there's already a negative sign here, so this becomes a positive sign. And so then the left-hand side just becomes alpha times... one over this plus h minus this equals, and the right hand side is still the same, natural log of we can simplify the stuff in here probably a little bit too so it doesn't look so bad. So it's like alpha times RE minus RE plus H all divided by RE plus H. So this becomes alpha times negative H, right? So negative alpha H over and then we get an answer then from this, which is going to be that P prime is going to be equal to e to the negative, or whoops, equals P naught e to the negative alpha H divided by it's basically the same answer though, because RE plus H, even if you're at the very tip top of our atmosphere, the height would be very small relative to the radius, but nonetheless, there you go. There's the answer. Get an H here and you get an H there. What does this one look like? It's pretty much going to look exactly the same, but we could plot it. Like, we could technically plot it. We need to calculate alpha. You guys could do this in Wolfram Alpha if you want to. We've got a little bit of time. I guess we can do it. Let's calculate what some of these numbers are here. So what's alpha equal to? So alpha is going to be... So molar mass was 28.8 times 10 to the minus 3. Here, let's do all this on the screen so you guys see what I'm doing. Okay, so we'll just pull this one, make this a little smaller. So we need to do molar mass, which is 28.8 times 10 to the minus 3, times big G, which is the gravitational constant from Newton, from Cavendish, and then times the mass of the Earth. Mass of the Earth is about 6 times 10 to the 24. We divide by R, which we would put into the 8.31 joule per mole Kelvin. We divide by the temperature. We're assuming the temperature is constant at 0, which was 273. So alpha is this big number. It's 3.6. So it's 5.1 times 10 to the 9, I think, right? Okay. And then we've got radius of the Earth, all that other stuff here. So now we want to go to Wolfram Alpha. Should let us plot this without a problem. All right, so here we go. So we're going to plot. So P naught was about 1 times 10 to the 5. Ooh, does it let me do that? Can I just write 1e5? Will it know what that means? I don't know. What do you guys think? Here, let's try something. I'm just curious. It knows what it means. Yeah, it knows what it means. Okay. I thought it did. So plot, we need to do, so that's 1e5. It's just an overall constant, so it's not that important, actually. We can leave that part out. That's just going to scale it, right? Whatever. And then times exp. So this is negative alpha, which is 5.1 E9, times y, so that's our variable. And we divide that by the radius of the Earth, which is 6.4 times 10 to the 6th. We also divide that by
the radius of the Earth plus y. So 6.4. The biggest thing here is that because the radius of the Earth is so extremely large, it's going to make it so that no, it's going to make it so that this is going to reduce down to RE plus H is basically going to be equal to RE, is what I'm saying, you know? Because this is going to be on the order of millions, while this is going to be on the order of thousands. But so we're only going to plot this from y equal to 0 to... What's the top of the... It's like 30 kilometers to the top of the atmosphere, right? So let's go up to the top of the atmosphere. We'll go to 30,000. I think that number is correct. Now let's see if it... Exponential is e to the power of all this junk. Negative 5.1, that was alpha times y, divided by 6.4, and then you divide again, it puts in the denominator too. So that looks... This looks like it's going to plot the right thing. Let's see if it understands what we did. Or if it just, like, just gets confused. Okay. This looks right? That looks right, actually. Hey, look, it looks exactly the same. And it has to, because the biggest issue here is that the radius of the Earth relative to the distance over which we're looking, right? So look, 6.4 times 10 to the 6th. This is 3 times 10 to the 5. No, 3 times 10 to the 4. So it only alters this digit right here, the digit after the 4. Yeah? That's all that's going to change. So what if we were to go... What if we assume that our planet had an atmosphere that went much higher? So what if we go out to double... This is where it might actually look a little bit different. What if we go out to double the atmosphere of the Earth? So we do 2 times 6.4, so 128, right? So we'll do 12.8. We'll go out to double the radius, triple. This would be triple the radius of the Earth, right? Above the altitude, right? Okay. So let's see what that gives us. So you can't even see the feature here anymore. Okay, so we need to go a little bit smaller. Let's go 5. That's really funny. I'm sure we could have zoomed in on that and figured out what was going on. Yeah, I mean, it's the same feature. It's just that, you know, the pressure's still 0, though, right? We'd have to do a log. We have to do a log plot. Will it do log plot? I don't know if it'll do it. I can't remember the... There you go. It's a straight line. It should be a straight line. But now you can see it's going over several orders of magnitude, right? 10 to the negative 7, 10 to the negative 16, 10 to the 27 to get up there. So, you guys remember log plots from your Physics 1A class? All right, so this is all I've got for today. We're going to stop for now.